Okay, let's be real for a second. Walking into your first embedded systems interview can feel, well, it can feel like you're trying to defuse a bomb, right? There's a ton of pressure, so many different concepts you have to juggle. That's exactly why we've put together this guide. We're going to walk through the core ideas, get that confidence up, and help you crack the code.
I think the worst part is just not knowing what to expect. But what if you knew the key questions they're almost guaranteed to ask? And even better, what if you really understood the concepts behind those questions? Well, that's exactly what we're about to do. We're going to break it all down and turn that anxiety into some solid, well-earned confidence.
All right, so here's our game plan for this. We're going to start with the absolute foundation, C language essentials. From there, we'll build up to operating system fundamentals. Then we'll take a really deep dive into embedded Linux. And finally, we'll wrap things up by comparing the different hardware architectures that make all this stuff run. Sound good? Let's do it.
Okay, Section 1, C language essentials. So why are we starting here? Simple. C is the language of hardware. It's how we talk directly to the silicon. Interviewers are going to grill you on this stuff because they need to know you get that fundamental connection between the code you write and the hardware that runs it. First up, volatile. This is a classic, and you're almost guaranteed to see it. So what's the deal? At its core, volatile is you telling the compiler, hey, don't get clever with this variable. You see, compilers are obsessed with optimization. They might think, oh, I already know what's in that memory location. I don't need to read it again. But volatile forces it to go and read from or write to memory every single time because something outside your code, like a piece of hardware or an interrupt, could have changed that value behind its back. It's absolutely crucial.
Next, let's talk about static versus global functions. Honestly, this all comes down to one big idea: scope. It's about keeping your code organized and preventing total chaos, especially in big projects. A static function is basically a private helper, right? It's only visible inside the 1.c file where you defined it. No other file can see it or call it. A global function, on the other hand, is out there for the whole world, or, the whole project, to see. Using static wherever you can is a huge green flag for an interviewer. It shows you write clean, maintainable code.
All right, on to Section 2, operating system fundamentals. So now we're kind of zooming out. We're moving from how a single piece of code works to how the entire system is managed. And let me tell you, getting these concepts right, this is what separates a good interview from a great one.
And I love this car analogy because it just makes the difference between an RTOS and a GPOS so incredibly clear. Think about it. An RTOS is like your car's airbag system. It's not about being fast on average. It's about having an absolutely guaranteed deadline. It must react in a few milliseconds, period. A GPOS, on the other hand, that's your infotainment system. It's built for good average performance. If it takes an extra second to load your playlist, no big deal, right? The stakes are totally different. And this table really lays it all out. But if you look at just one row, look at failure case. For an RTOS, missing a deadline is the failure. The whole system has failed. For a GPOS, a failure might just be a single app crashing. It all comes back to those two key words. An RTOS is designed for determinism, meeting deadlines, while a GPOS is designed for throughput, getting a lot of stuff done on average. Two totally different worlds.
Okay, let's tackle a really, really important concept. This next question is one of those things that immediately tells an interviewer if you're coming from a small microcontroller world or a bigger application processor world. So the question is, when you write a C program on, say, Linux, does it access the physical RAM chips directly? And the answer on any modern OS, like Linux, is a resounding no. Absolutely not. Your program doesn't live in the real world of physical RAM. It lives in its own little bubble called virtual memory. And this P.O. box analogy, it's perfect. Every single program gets its own private set of P.O. boxes. Your apps box number 100 has absolutely nothing to do with my apps box number 100. They are completely separate.
So what's the magic behind this? Well, it's not actually magic. It's a specific piece of hardware called the Memory Management Unit, or MMU for short. The MMU is like a super fast clerk at that post office. Your program says, I need what's in P.O. Box 100, and the MMU looks at its secret map, translates that to a real street address in physical RAM, and fetches the data. It's that constant translation that builds an impenetrable wall between applications.
So a cool thing happens when your program asks for a virtual address that isn't actually loaded into RAM yet. The MMU tries to do the translation, finds nothing, and triggers something called a page fault. Now, the word fault sounds bad, but in this case, it's totally normal. It's how Linux works. The kernel catches that fault, says, oh, you need that piece of the program, hold on, pulls that 4 kilobyte page from the disk, sticks it into RAM, updates its maps, and then lets your program continue. Your program has no idea anything even happened. It's brilliant lazy loading, and it's why huge apps can start up almost instantly.
This, on the other hand, is the one you don't want to see, the segmentation fault. A seg fault is a real error. Going back to our analogy, this is your program trying to access a PO box that was never assigned to it. It's an illegal memory access. The MMU catches it instantly, tells the kernel, and the kernel's response is swift and brutal. It terminates your process. It has to protect the integrity of the entire system.
Okay, Section 3, an embedded Linux deep dive. We've got all these great OS concepts down, like virtual memory and all that, but how does it all get started? Let's walk through the process of how an embedded Linux system actually boots up, from the very first instruction to a fully running system. But before we can talk about boot, we have to understand this absolutely critical separation: kernel space versus user space. Think of kernel space as the realm of the gods. It has unrestricted total access to all the hardware. A crash here, game over, the whole system goes down. User space, that's where all your normal applications live, in a nice, safe, protected area. A crash here just kills that one app. And the only way an app in user space can access hardware is to make a formal, very controlled request to the kernel. That request is called a system call. And this is the chain of events. It's a really cool handoff process. First, the CPU wakes up and runs a tiny piece of code from an internal unchangeable ROM. Its only job is to find the bootloader. Then, the bootloader, something like U-boot, takes over. It gets the RAM running and does other critical hardware setup. Its main job, though, is to load the Linux kernel and something called a device tree blob into RAM. Once that's done, the kernel takes control. It uncompresses itself, figures out what hardware it's running on, mounts the root file system where all your apps live, and finally, it runs the very first program, called init, which then kicks off everything else. It's a beautiful cascade.
Now, that little thing I mentioned, the device tree blob, or DTB, it's super important. How does the kernel know if it's running on a Raspberry Pi or some custom board? The device tree tells it. It's literally a data file that describes the hardware on the board. And here's why that's a game changer. It decouples the hardware description from the kernel code itself. This means you can take the exact same compiled kernel and run it on a bunch of different boards, just by giving it a different device tree file at boot. It's unbelievably powerful and efficient.
All right, for our final section, let's get right down to the metal, the hardware architectures themselves. We've talked a lot about the software, but now let's look at the different types of processors that actually run it. Understanding the why, the design philosophy behind these cores, will really make you stand out. First up, we have the ARM Cortex-M. Think of this as the real-time workhorse. It's a microcontroller core, and it is laser-focused on low power and deterministic behavior. This is what you'd use for motor control or reading a sensor, things that need to happen on a strict, predictable schedule. It often runs bare metal code or an RTOS, and one of its secret weapons is the NVIC, a piece of hardware designed for super fast and efficient interrupt handling. Then you have the ARM Cortex-A. This is the application powerhouse, and its superpower, the MMU, that memory management unit we just talked about, that's the defining feature of a Cortex-A. That's the piece of hardware that enables all the magic of virtual memory and lets you run a rich, complex operating system like Linux. You find these in smartphones, car infotainment systems, anything that needs serious processing power and a full OS. And finally, let's talk about the open source challenger RISC-V. Now, this one's a little different. RISC-V isn't a single processor design from one company. It's an open source instruction set architecture, or ISA. Think of it as a public rulebook for how a processor should work. The biggest deal here is freedom and customization. Companies don't have to pay royalties to use the base ISA, and, this is huge, they can add their own custom instructions to accelerate specific tasks. It's all about flexibility. So this table is a great way to see it all at a glance. You can see the key goal for each one: determinism for Cortex-M, high performance for Cortex-A, and flexibility for RISC-V. You see it in their memory hardware. The Cortex-M usually has a simpler memory protection unit, or MPU, while the Cortex-A has that full-blown MMU for virtual memory. And then, of course, you see that huge difference in the business model, which is really what's fueling the incredible amount of interest in RISC-V right now. And there you have it. From the C language essentials to the magic of virtual memory,
all the way through the Linux boot process and the hardware it runs on. The goal here isn't just for you to be able to answer isolated questions. It's to be able to connect the dots, to explain how volatile relates to hardware, how the MMU enables user space, and why you choose a Cortex-M over a Cortex-A. You're not just ready to answer questions, you're ready to have a real technical conversation. So, which concept are you going to bring up first? Good luck. You've got this.